Good afternoon. So if you want to join present live, you can scan the QR code. 1, 2, 4. So let us continue. That's why we finished the discussion. We have 2 problems, right? And 1.17, if we have FDMA and if we have TDMA with 8-way time multiplexing. And so that we are asked to have the number of simultaneous codes. And next one, we are asked to have the result for MN1. And if we double the rate, arrival and service rate, and then what are or how are system length and system time changed? Of course, this one finished, so let us check the reference solution. All right, so you have the solutions, but what are the correct solutions? So this one, let me check this for you. First of all, this one, you can check it. And maybe I remember one of you make sure, oh, okay, even we have the given number of codes, we reserve 1, so -1, so that we have 660 -1. That one is still okay because you mentioned we need to reserve some codes for the management. So first one, A, because of FDMA, so we have the frequency over the frequency band 25. All right, and because of full duplex, so full duplex over, so full duplex for each one, and then we have the simultaneous code. So the current channel over these, because of 2 duplex channel, simplex channel, and so therefore duplex voice channel. So this one and over 2. So we have this one. And the second one actually is simple because 8-way time multiplexing, so times 8. Well, so this is a reference solution for this problem. Is it okay? All right. And actually, you can get back to check the video so you will have the answer. If you want to keep this one easily, so you can take a picture. So if you want to do so, you can take a picture for the solution to problem 1.17. Well, is it okay? So no problem, then we move on to the next one. And this one, we don't have the solution directly, but actually we should check the formula. All right, so you can check the formula for system length and check formula for time. Well, so actually later you can look at the formula. Actually for the formula we have a rate, over rate and service rate. If we double, then we can cancel if we double rate and service rate. So this one, okay, no problem. So same, but time, because we have it's half. But time, actually we don't have the rate in the numerator, so we will have the original time. So this one you can check the formula. And actually I remember that time the presenter showed the formula and so that the result can be shown easily, right? All right, so that's it. This is the second problem. All right, almost all, and let us continue the discussion today. So before we continue here, I already have the questionnaires, and let me know the status of you about the current EMI course. So first question, up to now, how do you feel about our EMI course? I don't have the specific meaning for this, but I think you will understand what it means. So that I have 1 minute for each question. All right, that's okay, no problem. Yeah, maybe some of you perhaps feel somehow worried. Near 20%. Fine, no problem. All right, let me check, not finished. If finished, then we can continue. So let me move on to the next one. If not finished, you just let me know. And how about the path of lecturing? Yeah, some of you feel, okay, too slow. And most of you feel, okay, that's good. Well, same, let me make sure not finished. Okay, let me move on to the next one. And actually, for Taiwanese, you should understand we have some resources in Chinese. And for the other students, oh, okay, some of you failed to notice this. We have a video on YouTube in Chinese, so you can refer to those if you need them. And for videos of current lecturing, currently I have the videos using streaming, so you can check the playlist or streaming. But sometimes I will add video to the playlist a few days or a few weeks later. If you want to check that immediately, you can try to check stream videos on my YouTube channel. So maybe some of you failed to notice this. So that's why I want to let you know, yes, we have the actual resources. Well, not finished? All right, so it's okay. Some of the questions somewhat like serving as reminders. And how about the resources? And are these resources helpful to you? So finish. Oh, okay. So even some of you fail to notice, but all of you agree with these. These resources are helpful. Okay, good. And if any possible help you still need, maybe you can let me know. And actually, let you know, all the questions here will still collect the points for you. Each one, 2 points. All right, so for this one, %, well understood. Oh, 30%. And most of you feel so far so good. All right. But why none of the above? Actually, the current choices, some serving as good and some serving as bad, or so far so good since oh, okay, it's fail. And I'm curious about the item here. Some of you think, oh, okay, none of the above. So any possible idea about this? Why none of the above? If you choose that one, can you share your idea with me? Maybe no. Okay, fine. All right, Sam, finish or not finish? Okay, seems to be okay. Let me move on to the next one. Finally, this one. Even we do not heavily rely on this, but we have a free classroom teaching. For example, that time we ask you to have the video viewing first before you come to the classroom, right? And it doesn't mean I will frequently rely on this, but at least we have one possible item like this. Can this accepted by you? So can you see? No? So let me retry this. So you can accept, that's good. And again, let me make sure, not finished. Okay, so almost finished. And let me try this again. And about this, can you have it? Your suggestions? No? Actually, the first one, maybe many days ago or maybe many weeks ago, he or she answered. But currently, no. Okay, fine. All right, so, okay. All right, so if no, maybe I just follow the current way to have the EMI courses, and hopefully you still can find it's helpful, or maybe it's okay for you. So, done for all of you. Oh, if so finish for this. Therefore, finally, this one, it's a different one. Previously, I use those serve as the activities, but this one for attendance checking. So same scan, and you can put your ID and the name on all everywhere. Okay, go and finish this. So we have 12, but here we have 14. So not finished? Okay, so let me go to the next one. All right, so last week we finished the discussion using Jigsaw. Jigsaw to talk about the propagation mechanism. So anyone still remember 3 propagation mechanisms there? If yes, raise your hands. Of course, allow you to be the presenter to answer the current question. Even I don't pose a question here. 3 mechanisms of propagation. 3. Anyone want to try to answer my current question? Sure, allow you to check your slides. So any 3 mechanisms? And I did, okay. Alice, right? So wait a moment. Allow you to answer, wait a moment. Ready, go. Louder, speak louder. Scattering, reflection, and diffraction. Yes, correct. Reflection first, diffraction, and scattering. If I follow the order of slides, right? Okay, so you can indicate you are the presenter, all right, on line group, and so the tutor will collect that for you. So it's clear, and after finishing that one, propagation mechanism, and right now, data check effect. All right, so right now we have all of the mechanism to have the effects. The red one, so the normal one, right? And this one, reflected signal. So because of a reflection, therefore we have the effect from reflection. And the diffracted signal. And also scatter signal. Therefore, still based on the 3 mechanisms to have the scatter signals, diffracted signals, and the reflected signal. And don't forget, do we expect scatter signals, diffracted signals, and reflected signals to interfere the original desired signal? Here, it's the direct signal. No, right? However, the other signal even comes from the same source. However, will be received at the same site. At the same site, of course, we will have the undesired signals from reflected one, diffracted one, scattered one, and so that even coming from the same source, these serving as the interference. All right, so here we will have an interference if we have the propagation effects. Well, how to have the further capturing? So we want to check maybe from the simple one, then to have a bit more complicated one, so that we have the first case, free space propagation, and so that we just consider, oh, okay, we can propagate and receive signal at a distance d, and then what's the power? The power follows the formula, and we have some constant or parameter. And P sub T means the power of a transmitter, and P sub R means the power of a receiver. And for D actually is distance. So we will have something like it's a principle. The power will decay as actually maybe with the distance, and it's inverse proportional to difference, and it's d squared. So we have all these. As for the others, I think we think there are some possible constants. Even we can have the name. But I skip the details and let you know, oh, okay, initially we will have the attenuation effect caused by distance. And here, this is a free space propagation. And of course, we can have the others, because later we will have some further details for the other models. Well, here we talk about antenna gain, and antenna gain follow the possible formula. You just check it, and I allow you to have 2 minutes to check it. Even we don't have the discussion directly, but these are given formula. You just follow the given formula, and then what is the gain? Just calculate these. So that you have 2 minutes to check this page. Just a formula. So current discussion, I mean the current content here, just allow you to have the calculation. Gain, G. So almost near 2 minutes, but finally, oh, okay, we can have a formula. So why we have the formula? It doesn't mean we should check this, but at least we have the formula. And finally, based on the formula here, if we can have the proper way to change it, oh, okay, we care about frequency. So what is the relationship of gain and the frequency here? Oh, look at this. Gain actually proportional to the frequency, and proportional to frequency squared. That's why higher the frequency and higher the gain. So this is the observation if we have a formula. And because of this, we can have the higher gain. So normally, if we want to have the transmission, it doesn't mean we want to stay within the lower frequency band. In fact, we expect to have the higher frequency band to have the transmission because of higher gain. All right, so that's why we need to move maybe signal within the baseband, lower frequency band to the higher frequency band, and so that we can have a higher antenna gain to achieve the high efficiency. All right, so the fact here, I emphasize the fact here, as for the formula, actually, we don't have any specific reason to explain. Maybe if you have some chance to study antenna, and then you will know the formula. But we just apply, and so that we can have the induce something like conclusion. Higher the frequency and higher will be the gain for some given antenna size. All right, so this one just serving as the reference. So we have the propagation through distance and the effect through distance. And later we want to have a different formula, and this formula says, of course, we can have a gain at the transmitter and gain at the receiver. And of course, initially we have the transmit power, and so that we have the receive power. And up to now, it seems to be we want to enhance it, so we have a gain. The gain try to amplify, to enhance it, but only gain. In fact, we have a loss. So actually, we have L. At L here, we have the accumulation of 3 possible losses. First of all, path loss. Path loss says, oh, as distance, as actually, if we have a distance, if you move and then longer distance cause the path loss. And then we have slow fading and fast fading. These cause to loss as well. So we have 3 different terms. And 3 different terms, why? L is the multiplication of the 3 factors. Because we want to accumulate. Well, maybe you have a question. Accumulate, but why it's the multiplication? Actually, if we talk about the real calculation, yes, gain, multiply. So loss actually divided and divided and divided. So we have 3 different terms. And if we have the different way to calculate gain and loss, for example, we can use log. If we want to measure loss or gain in terms of a log, then we will have a sum of the possible terms. But currently, they are absolute values, so we don't have any specific manipulation. Therefore, we have the multiplication directly rather than sum of all the terms. And in the exercise, sometimes we use dB, decibel. dB, then we can have the log included in the manipulation so that we can change the current operation into the form of sum. But right now, no, we have the original value or the absolute value. So we have the multiplication for all losses and multiplication for all gains. All right, so this one. And later we want to separate the 3 effects or 3 types of losses into the individual one, and want to check, or we want to investigate how to have the individual effect. Why we have the individual effect? Well, for the loss, we have the multiplication directly. So that way allow us to have the individual investigation. That's why we start from path loss first. You see what that means? Path loss. Signal strength decays exponentially with the distance d between the transmitter and the receiver. And this one we call the path loss because we have a path. As if we move further to leave the current, maybe it's the receiver. Move and to a different distance d, and then we will have a loss caused by distance d. And this kind of loss, of course, it is called path loss. And if we want to have the path loss under the effect of distance, then it's really simple. Let us have the transmitted power and over received power. Then we will have a loss. And if we want to have a gain, actually it should be received power over the transmitted one. But even we have that one, it doesn't mean zero or none of the losses. So therefore, we investigate losses first. And this one actually, someone based on the field trials and saw that they can have some experiment result. Once they have the experiment result, they found some relationship. First of all, loss. The path loss actually related to distance only. Previously, it says yes, so we know the possible term causing by distance, d. And only distance, no. This one still depends on frequency, carrier frequency. So if we have the large carrier frequency, then we will have a high value of path loss as well. Why? Higher than we have the path loss. If we have a high frequency, based on the formula, speed equal to frequency multiplied wavelength. So high frequency, then we have a really short wavelength. Really short wavelength, then it will incur possible blocking by any buildings. So of course, if we have a large frequency, then we will bring the path loss for sure. But follow the current formula. All right, so we have these. And it says, well, if we have all these, depends on distance and also depends on carrier frequency. And then we have the path loss. And so that it says, oh, previously we just care about distance, but how about frequency? Yes, frequency depends as well. Therefore, we have a highlight here. And we also mentioned this one. Well, we know d squared, but don't forget, previously d squared for which model? Free space, right? And right now, if we have the communication, for example, in metropolitan area, and also consider a different scenario. Oh, okay, maybe we have a really wide area without any buildings, and if you consider that case, so since that one applied to free space, but right now if we consider metropolitan area, then it doesn't mean d squared, perhaps d squared to, for example, d raised power to 2.5, 3, and actually can be 4. If we have a d squared, it says, okay, the effect not so serious. But d raised power to 4, and this one is really serious. So this is the environment, for example, in metropolitan area, because we have many interferences, so that include those, and so that how about the loss coming from the path loss? Yes, even higher if we don't think d squared can reflect the facts. We will change it to d, for example, 3, and d 4. It's possible. So depending on the environment, then we will have the exponent of distance. So this one as well. And for the current formula, if we have a free space, why this one different from the previous one? In fact, this is the actually the field trial. Field trial, of course, we have the possible terms after trial. So this one, it should be the exact one, but the previous one is the simplified one. So the previous one, we do not have the formula like this. And here, we use it to serve as the pass loads in free space. Well, again, we still have the pass loads. And pass loads d squared, no, right now we have d raised power to alpha. And alpha actually is the propagation constant. And the value for alpha, if we do not consider free space, normally we should have 3 or 4 for urban area. Right? I don't know, metropolitan area, we will have the severe effects coming from pass loads. So of course, we should have the exponent raising from 2, for example, to the current one, 3 or 4 for the typical urban area. All right, that's it. So let me stop here temporarily and allow you to have the short discussion and thinking about currently what we reach and how we have the possible conclusions. All right, so maybe let me check the seats again. And for group 4, it's okay, just get closer. All right, so no problem, no need to change. And for group 1, yeah, you can get closer to have the possible discussion. And for Jen, your name Jen? Okay. Is it okay? Okay, sure. And feel free to have the discussion for the current items. And you can get closer. So I rather have 3 minutes to discuss, and later, if no question, then I can move on to the next one. Okay, so the current activity in the past are simply called turn and talk. And turn and talk actually allow you to have the chance to have further discussion with your teammates. And then you can refresh something and so that you won't fall asleep, right? So it's called a turn and talk, but that's a matter. I try to have a questionnaire. Do you think turn and talk efficient? They don't have any idea. And so that this time I didn't know the meaning, what that means, turn and talk. All right, so turn and talk maybe, oh, okay, don't waste time. Continue. If I continue, perhaps you fall asleep. All right, so even we can pause, allow you to have a chance to think. A chance to think. It's the pedagogy. All right, so even pause and then you have something to think. But let me check. Up to now, any questions? So if no, here, alpha 3 to 4, right, in urban area. And so that I have a question. How about alpha in a suburban area? Similar to 3 to 4 or lower? I can't call suburban area. Here it's urban area, so suburban area, it doesn't mean the free space. So that value should be comparable value like the urban area or a bit lower. To try to guess. Comparable, lower, or maybe higher. Which one you think? Lower. Yeah, lower. Okay, agree. So yes, it's true. If we have, if we don't have any, even no buildings, just trees, that's okay. So the value should be a bit lower, perhaps 2.5 or something else. But for free space, and then it's 2. All right, so this one. And the current formula, you see, it's the simplest formula. If we don't care about the others, we just care about distance. And then pass loads depends on distance. But previously, we have the formula depends on carrier frequency. So it doesn't mean purely depends on distance. But distance and the frequency are almost the same. They have the proportional way. So in terms of first of all, in terms of the current formula, actually, all frequency and distance almost the same way, right? But dB actually it doesn't mean the pure quantity. We try to transform, for example, oh, okay, so the pure one, but we try to change it to, for example, and this one is called dB. All right, so dB actually will have a logarithm. Base is 10. And we have this and multiply 20. So we have the dB. And if we have log and multiply the previous one, so it should be, oh, this one multiplied the frequency and the distance. All right, so we have this. And actually, I don't know if we have the way to have the calculation. Perhaps we can collect sum rather than the multiplication. But we want to have the pure quantity. Based on the current formula, it should be the multiplication from frequency and the distance simultaneously. So both carrier frequency and distance affects the loads, the path loads. So I emphasize dB. And later we show all the results in terms of dB, decibel. And the decibel, then first of all, we show the current figure like this. First of all, look at this. Frequency here. So from the first one to this one, what it means? Low frequency and high frequency. And high frequency here. So loss is high or low. Previously, we have a formula related to frequency. Higher frequency cause high path loss. So the current one actually shows the first one as frequency becomes higher, then we have a high path loss. And how about this and D? Increase D, actually the increasing trend. So the current figure actually we illustrate the relationship path loss related to carrier frequency and the distance. And right now in free space. So the current one, something like we collect data and maybe we have for the experiment collect data so we can show the current figure. And let us have the quick look at this. And keep in mind, okay, the label here, lower than 130, right? So urban area. At least higher than 130. So we will have an even worse situation considered later. And we may have an urban area. Of course, we can have a suburban area. And later we can try to check, oh, okay, if we have the same one, but what's the path loss for different scenario? So later we will check it, but let us get back to this one first. All right, so currently we already have the trend. So the current trend actually covered by that equation to simultaneously illustrate frequency, carrier frequency, and the distance can affect the path loss. All right, that's it. So let me Marshall, any questions? If no, take a rest first for 10 minutes. So before we go, if you want to scan this, go ahead and join Present Live later. So if not, then we move on to the next one. So we have the free space example. And later we will check the others. So the others actually we have an urban area, it's large city. And urban area is a medium small city, and suburban area and open area. So the trend here, actually the worst case in large city, then the open area if we don't have the free space. And previously I asked you this equation, suburban area, right? So suburban area we still have the trees, and so of course we still have the possible obstacle, and it's not easy to have the perfect transmission or propagation. So suburban area get even better, but still worse than the open area. So first of all, same. Some researchers try to have the possible parameters here, and so that we have the formula. To have the formula here, look at this. We have a carrier frequency. All right, we have a distance. And also previously we have H base station, height of the base station, and height of the mobile station. And also we have the specific function alpha. And specific function alpha, then we have the differentiation. Oh, for these, alpha actually depends on large city or small or medium city. And so that we have almost the same formula, but we can distinguish using alpha of H sub n. And for these, actually we can have two cases, large city and small or medium city. As for suburban area, seems to be neater. We have the original pure free space to have the formula, but minus. And for open area, oh sorry, this one should be the previous one, but minus and minus. And here we have plus as well. So it doesn't mean plus and then increase. So increase further for suburban area, and for open area. Later we can check the figure, then you can know, okay, the final one should be the lowest one if we talk about path loads. Yes, for the first one, urban area, large city. So you can check the value here. Approximately it's 175, right? And this one, comparable. Wait a moment, comparable. Sorry, a different color. So first of all, check the color. All right, so this one, highest frequency here. So 1,500. Here, this one, but different color, but same this one, so comparable. And for this one, actually, we can have the difference. Suburban area, so this one, 1,500, this one, the value at this lower than the previous two cases. And also check the next one. Open area, yes, it's, for example, 143. And this one approximately should be, more than 160. So of course, decrease further to the open area. All right, that's it. So the current discussion, we talk about path loads. And path loads actually depends on the area you have. Maybe metropolitan area, suburban area, or open area, or free space. And actually, I think if I follow the current way, then you know if we check losses, specifically the path losses, actually the first one, the most serious one, and the final one actually you will have less path loss effect. All right, that's it. Path loss. Think about this. Any questions? And then you have 2 minutes to think about this. And feel free to discuss with your neighbors.
Okay, so before I continue, any questions? No, so let me move on to the next one. So actually, we have 3 types of losses. The first one, pass loss, but right now, let's check slow fading and fast fading. So slow fading, we call it long-term fading. So that you know, okay, after long-term, then we will have a change, so it's long-term fading. And the fast fading actually is the short-term fading. And so that we have the further fluctuations. Of course, right now we have the way of changes, so we can see all the parts of the changes. If we check the scale, something like the scale, the smallest one, and the scale a bit larger, and the scale for really large. And so we have the 3 types of losses, from pass loss to slow fading to fast fading. Well, fade, what it means here. If we talk about trends, actually trends will decrease gradually, and this is called fade. And we have the effect, so we call fading. Because we discussed pass loss in the past section, but right now let us continue to check the second one, slow fading. So slow fading here. So you can check what it means, slow fading. Caused by movement over distance. And the distance actually large enough to produce growth variation. And so that this one, it is called slow fading. And also called the long-term variation. And so that we have the corresponding description later. And this one is long-term, and we also call it sharing or log normal fading. All right. If we talk about the second term sharing or the corresponding one, we will have the log normal to be included to describe the signal changes. And so that here we have the log normal distribution. The log normal distribution used to describe the signal label. All right, so log normal. What's the form for log normal? First, we talk about the probability theory. So we know log normal, right? And here, let me ask you the question. The current form you have, it's normal or log normal? The current form here is normal or log normal? If you think it's normal, raise your hands. Log normal? The answer is normal. Now, why log normal? If we have the original quantity, taking logarithm first to have the value in terms of logarithm, then using logarithm to check the distribution. If logarithm follows normal, then this kind of distribution we call log normal. So log normal, something like we have the operation inside the name, taking logarithm, then follows normal distribution. And so this kind of signal distribution should follow the so-called log normal. So understand the meaning, I don't know, log normal. And the thing about this, why this one we have log because the current description in terms of decibels. Right? Decibels actually tackling logarithm first. Now, of course, because of logarithm, so log already here. And the normal, so we have a normal. And we have to have the log normal distribution. If we care about the original signal level, not in terms of decibels, and then that signal strength follows the log normal distribution. All right, so in fact, for the current signal we have, it follows log normal. However, for the current signal strength, if we take logarithm and then what's the distribution for the logarithm value of signal strength? It's normal. All right, so normal or not normal here. Can you tell which one is normal or which one is not normal? All right, so even I don't know the answer, but let me repeat the question again. If we consider signal strength without any decibels, this is the first type of a signal. And the second type of a signal is the signal strength taking logarithm. And so that we pass on the logarithm value, and then we have the corresponding distribution. So let me ask you, first of all, for first case, which distribution we have if we consider the shadowing or slow fading here? It's log normal or normal? It's log normal. But for the second one, taking logarithm already, so what is the distribution? It's normal. All right, so this is the way to have the log normal distribution. Well, so of course, normal can be shown easily. So we use normal, and we want to use it to describe the signal strength. Of course, we need to show all the signal level in terms of decibels, and so that we can have the log normal distribution. So shadowing actually says if you can have theory, actually we can have the formula to govern the signal strength. Kind of distribution to govern the signal strength, actually log normal to govern the signal strength. All right, what I mean shadow here. And currently same. Current shape, the bell shape is normal or log normal? The current bell shape is normal or log normal? Normal, correct. Okay, so allow you to serve as a presenter. Sure, go and allow the TA know. Yeah, it's normal. Because of normal, then we will have the bell shape. But why this one normal? Because we have signal level, but in dB. All right. However, if we don't want to have a dB using the original value to have the proper distribution, then what's the distribution? Anyone want to try? Yeah, log normal. So understand currently log normal and the normal relationship. All right, Sam, you can indicate you are the presenter. Well, so that's the shadowing, that's the slow fading. And fast fading, actually, we still can employ the other distribution to describe fast fading. And so we will have the later formula, but even complicated. But we check how to have a fast fading. Here it says, reflecting from objects, hills, buildings, vehicles, and this one is the normal one. Fast fading due to scattering of a signal by object near transmitter. All right, and how to have the signal strength distribution, actually we can have these. Receive signal, we can describe this by Rayleigh distribution. As for Rayleigh, actually from the probability theory, you can look up what it means, Rayleigh. And the Rayleigh here, actually we will have a beta equal to 0, so that it's Rayleigh. But the current formula, actually it should be Rayleigh formula. Alright, so Rayleigh, and then we can use them to describe the signal strength of the fast fading. And we have some parameter description. You can try to check these. Specifically, we relate some results to the Bessel function. Alright, so this is the result. So the other middle value, you can try to check middle. Alright. And here, actually, beta equal to 0, then we have a Rayleigh distribution. And Rayleigh distribution, if we further check parameter sigma, then we have further different envelope variation. Okay, like this one. So it doesn't mean we have beta equal to 0. If not 0, then we have this one. Oh, okay, and this kind of term then we call Rayleigh. And Rayleigh still related to 0 order Bessel function, like this way. Alright, so this is the Rayleigh. So Rayleigh and the Rayleigh, and normally actually we have the different application. Rayleigh actually talking about the mean, the label is non-zero. But for Rayleigh actually the mean is it's 0. So this is the difference. And so the Rayleigh we have the sharp envelope for the distribution. And previously we didn't know, oh okay, well, we have the Rayleigh actually when the parameter beta equal to 0, then that one is Rayleigh. So the others actually they are Rayleigh. So the parameter here except for beta equal to 0, the others actually follow the parameter of Rayleigh distribution. So all these serving as the distribution to allow us to have the description for the fast fading signal strength. Alright, that's it. So let me stop here, and because we have some definition. So maybe it doesn't mean I want to hurry up to go through all the slides in chapter 3. So let me stop and let you think about this one. Fading from it should be from even from pass loss to slow fading, finally to fast fading. So think about what kind of content you have, and also why finally we have the function Rayleigh, and the other function to describe fast fading. Okay, then you have 3 minutes to discuss with your neighbors. Okay, go and check it. If you want to have slides, we can have the slides on Moodle. You can download the slides from Moodle. Of course, I will update for you later for the other possible chapters. So even we still have 40 seconds, but let's check the next one. Oh, okay, if we care about signal level, so we have a characteristics of instantaneous amplitude. Instantaneous amplitude, then we care about the following terms. So we have some definition. We have a signal level.
We can set a level there. Can we have the possible times of level crossing? So that we have a level crossing rate. If a level crossing rate, what it means? Odd number of times per second that the signal ever cross the level specified in positive going direction. For example, positive, cross it, finally get back to negative and positive. So we care about one direction, positive going direction. And that way it is called the level crossing rate. This is the first one. So it doesn't mean, upward and then downward. No, just upward only. No downward here. And the second one, fading rate. Basically, we have the definition of a level middle. I don't mention middle, but you can follow the previous way to have the middle value. And we set the middle value as a level of to be crossed. And so that if we count the number of signal envelope crosses middle value in positive direction, and it's called the fading rate. Therefore, fading rate is a special case of the general level crossing rate. What kind of a level crossing rate? It should be the reference level be the middle level, and middle level to be crossed, and then it's the fading rate. And the depth of fading, then its ratio. There's someone like, we have the value. In fact, no, here, depth of fading is ratio. And ratio of mean square value and the minimum value of fading signal. So if we select one fading signal, and if we can find mean value and the minimum value, the ratio is called the depth of fading. Finally, the fading duration. The time interval for which signal, and it is below the specified threshold, and then this is called the fading duration. All right, allow you to have 2 minutes to think about the definition here. Level crossing rate, fading rate, depth of fading, and the fading duration. Likewise, we still have 30 seconds, but let me move on to the next page. This is called the frequency shift. And this kind of shift because of mobility and also the frequency. So we have the Doppler shift.
And Doppler effect, actually, you can check these. When one source and receiver, they are moving towards each other or something else, then the frequency of the received signal will be changed properly. The formula here, carrier frequency minus this one, and we have a V over lambda multiply the angle. It's a theta. And this way we call the Doppler shift, and so that you will have the frequency shift follow the principle, Doppler shift. Well, later we will use it, so you can check this one properly. So direction alpha there, the direction of a moving signal. And this is the speed. And so that we will have an angle. And for the formula here, actually, we try to have the way to increase or to decrease. We will follow the formula to have the calculation. And next one, moving spray effect. Spray, actually, we will spray to the out. So spray out. And why? Because we don't have the single path. We have the other propagation effect. So we have the shift to the other side. So we have the separation. So this kind of effect we call moving speed effect. And previously we have a delay spray. So delay spray, actually we have a different time to reach the destinations. Of course, this kind of effect we call the delay spray. And this kind of a delay spray. And delay spray actually can be sprayed to the other area, and this is called the frequency of delay spray. And here you let know, oh, okay, we have the different situation because of the refraction, etc. So we have the possible waveform coming from different reflectors. So for example, the signal from the close by reflectors, and this one is a medium reflector, and the other is far away reflectors. And this is inter-symbol interference. Well, inter-symbol interference, actually we have a symbol. The symbols won't affect the other, so that's the perfect design. But however, for the real situation, no. We will have the different waveforms put them together, so we have the received signal to become larger or become smaller. It really depends on the possible interference. So RSI actually inter-symbol, and the interference for the symbol will interfere that symbol, and this kind of interference we call inter-symbol interference. And actually to avoid inter-symbol interference, we should follow the relationship. So the rate is actually governed by the value, and the value actually is tau d. So this is a researcher's development to know the relationship, and we can follow a relationship to specify the possible tau d delay spray. All right, so again, let me stop here for you to have the discussion for some definition and some phenomena. Okay, go and check it with your classmates, with your teammates. All right, so maybe still have a few seconds. This one define coherence bandwidth.
So coherent bandwidth actually,
this is the different separation, this one. To study signal envelope at the different signal, and then the difference is called the coherence bandwidth. So for the others, I think you can check it. So what it means, coherence, this one, you can check the real meaning if you don't think this one fits the current discussion.
Well, co-channel actually in chapter 5, well, what do you know co-channel?
Co-channel says, oh, within the cell I use channel 1.
And the other cell also use the same, so we have the co-channel interference. So of course, co-channel interference, we should have the same frequency, interfere with each other, and later we will have some parameters. So this one, if we specify some threshold and the desired one, and if still low, and then this is a co-channel probability. Why a term co-channel probability? I don't have any idea, but if possible, you don't care about the name, you just care about the corresponding probability. And then we can find for example, for the company, of course, we don't. Actually, we don't have we expect we have the same one, so we don't have for this case and try to avoid it. But actually, we still incur this kind of interference, so we have for the setting. So this is the design one. Alright, and design one maybe specify the threshold still lower, then maybe you think this one still have for the interference or some other things. Oh, we can define this, and later we can have the corresponding formula. So, if we go through chapter 3 just talk about the terminologies, and think about these. Going through all the terminology, which one you think you know them well? So if yes, then you can put the term to the word cloud, and the word cloud will check your understanding about the terms of the chapter. And so I know you know that exactly, or you still need to refine to have the exact terms. Okay, then you have 2 minutes to think about the term and also key in the term, and finally you can have these. Before I go, let me make sure. Can you have the poll here? Can you see it? Okay, good. Yeah, pass those correct. And the fading duration. And we have the propagation to cause all the possible issues. And we have an antenna, and antenna can have the different gain. That's correct. And we have a fading. Fading can employ the distribution log normal. And log normal actually is the original term shadowing effect. Oh, okay. That's all, no problem. Almost known by you. So let me make sure not finished, raise your hands. All right, so finish for all of you. Then we move on to the next one.
So this is the content we describe. And later I try to assign the problem. Even later we don't have enough time, but someone serving as a preparation. Take a picture first. And then we have 10 minutes to have the discussion with your. Then we have A first. And then we assign. We have a 4. So, okay. Actually, we have 5 sub-problems. First one, let me assign to Group 2.
Group 2. First problem. And the third one, 3.9 by Group 1.
And so the sub-problem of the second problem A
and B by Group 3.
C
by Group 4.
And also we will have the answer for all of the questions. So I will ask you to share your reference solution, and besides you should understand how to have the answer for the other questions as well. But I assign some of the team to have the reference solution. If you think okay, you want to know all of this, sure, you can know. But initially try to figure out how to have the solution. Likewise, you can use ChatGPT to find the possible answer. Go and check it. 8 minutes. So if possible, you can try to rotate your table to have the other discussion. If you don't feel so sure, something at least you get closer, so you can have the way to have the proper discussion for sure, no problem. So actually for this one, well, you can have the formula. I mean, your problem, sub-problem C, right? So which formula you think can apply to the current problem? Yeah, sure. That's true. And how to apply, check it. Yeah, sure. Yes, of course, you can share information with your teammates. So I think you know where to have the formula, right? Fine. So the others, you should find the proper definition. Okay, go and check it. So for the assignment at this, you can prepare the reference solution. All right. Reference solution this Wednesday, I will ask the full presenter to provide the reference solution. And the final idea is for all of you to understand all the problems. So if there's any, you focus on that only. No, for all things. If you want to prepare the solution, and for yourself, sure, you can prepare. Summarize all of the problems here, serving as a self-exercise. Try to gather the solution, and so that you can upload the solution easy this Wednesday. All right, so that's it. You can look up the task book, but before you go, let me make sure first one. Any questions? No. Second one. Previously, I've asked some of the students to find the task book. So can you find the task book? No? Not yet, right? Okay. Or maybe the other guys, you can look up any possibility to find the task book, and so that it won't be necessary for you to buy. But it's a special track, so I cannot mention that explicitly. So if you have it, you can share with the other classmates. For me, of course, I have the task book, but for you, maybe no. However, if you want to know some detailed content, of course, you need to have the task book so that you can review. All right, that's all. The two questions, maybe the second one, perhaps you cannot find it. You still can try. And finally, hopefully you can have one task book for reference. If no further questions, thank you and see you this Wednesday. Bye-bye.